be familiar with them and the intent. Okay, this is a review of complex numbers. These are things that you should have seen before, maybe not necessarily mastered, but you should be familiar with them, and the intention of this is to refresh your memory of these important ideas. They will show up, at least for EEs and COEs, many times over throughout your training and your applications throughout your career. The reason that we have to use complex numbers, believe it or not, is to make things simpler. And as we go through the Chapter 8 stuff, hopefully you'll get an appreciation that by using complex numbers we can solve circuit problems, at least for the case of sinusoids, much easier than if we had to deal directly with the differential equation. So there's a price to pay. It's a small price. You have to learn to deal with complex numbers. They are not anything that's difficult. It just requires learning a few rules and learning how to apply them, and with a little practice each and every one of you can become a master at using complex numbers. But it does take a little bit of practice. Okay, so complex numbers historically arose when mathematicians realized that not every polynomial had roots that were real, and at the time real numbers were the only thing that mathematicians had envisioned, and therefore it was kind of odd for these polynomials to essentially not have solutions. So you might have something like x squared plus 1 is equal to 0, and that bothered mathematicians because you couldn't find a solution to that equation. And so some pioneering mathematician, I'm not sure exactly who it was, said, well, let's just invent a new number for which will be the solution to this, and that number was, mathematicians call it I, physicists call it I, electrical engineers, because there is current is used to represent, or I is used to represent current. We don't use I, we use J. So if J was defined to be the number that was the square root of minus 1, or in other words, J squared is equal to 1, so when we take J and we plug it into this equation, it satisfies that equation. So that's historically where they came from, and then over the period of 100 years or more, lots of additional theory and applications of complex numbers showed up. Now it should be no surprise that we've already seen complex numbers crop up once when we looked at our characteristic polynomial, say for example s squared plus a1s plus a0, something like that. I may have the subscripts in a slightly different form than what we saw before, but for a polynomial like that, that was the characteristic polynomial. If its roots were complex, we ended up getting oscillatory behavior of our part of our solution. And so we've already seen that show up once. What we want to do now is see how we can use the concept of complex numbers to make it easy to deal with circuits that have sinusoidal sources in them. So with this definition that J is equal to the square root of minus 1, or equivalently that J squared is equal to minus 1, we then can get that a minus J times a J gives us a minus J squared. So if J squared is minus 1, a minus J squared must be plus 1. And likewise, minus J times minus J. Well, the minuses cancel each other, and we end up with J squared again, which is minus 1. So those are just the fundamental properties, and really you just have to, you don't have to memorize them. All of that actually comes from just this one definition. So if you can just remember J squared is equal to minus 1, everything else can be puzzled out of that. Well, not everything else, but all this other stuff in this box can be puzzled from that. So this box here is pointing out what I was saying a minute ago, that we've already encountered these, although we quickly dispensed with having to deal with them directly. You now know that when you have a situation where your roots are complex, you can handle it by dealing with the zeta and the omegas of n and putting it into the form where you have an exponential and the sine and the cosine and so forth. And so you don't have to deal directly with the complex forms, but you should be aware that those things are underlying that form of solution. So when you have an underdamped circuit, there really is some complex numbers going on underneath all of that. Okay, so what we've been talking about so far are imaginary numbers. J is an imaginary number, and j times anything else is imaginary. So we could have j5 is imaginary, and if we were to take and square that, we would get j squared times 5 squared, so that's minus 25. And so that's how the imaginary numbers work. If we integrate the imaginary numbers in with the real numbers, we can combine them together, but we need to keep them separate. So we combine them in a way that says, well, we could take a real number and we could take an imaginary number and add them together to create a complex number. And that also comes from the fact that some solutions to polynomials, or some roots of polynomials, end up not having purely imaginary forms, but have form that requires a real plus an imaginary number. And so we could then look at a plus jb and say, let's square that. And so what does that mean? Well, it's going to be a plus jb times a plus jb. And now, treating that as the product of the sum of two things, we can expand that out and we get a times a. We get an a times jb plus another a times jb plus a jb squared, and we know how each one of those things works, and so forth. So this is the next logical step here, to write things as a complex number being the sum of a real number plus an imaginary number, which is really nothing more than b is a real number times j, which is the building block for all imaginary numbers. So the important thing is that in order to be in this form, what we call rectangular form, we'll see why it's called rectangular form in just a little bit, a and b themselves must be real numbers. And another important thing is that when we take z, which is this complex number written in this form, and we use the symbol real of z, what we get is the real part. And now listen carefully, this is the just a little trick here, a little tricky. If we take the imaginary part of z, we don't get jb, we just get b. Okay, so that's just a matter of notation and convention. So our rules for multiplying and adding complex numbers, at least in this form, rectangular form, in a minute we'll see polar form, which you've seen before, but we'll reintroduce. So addition is easy to do in rectangular form. So here's one complex number, here's another complex number. We could call this z1 and z2. So if we add z1 and z2, the real parts add and the imaginary parts add. So we have a plus z is the real part, we have a j out in front times b plus d is the imaginary part. So that's for addition. If we're going to do z1 times z2, then as we did up above, we have to multiply these things term by term, just like we would multiply any two things that are the sum of two parts. And this negative sign here comes from the jb times the jd. You get a j squared is equal to the minus 1, so that minus 1 gives us that minus sign there. So you should have seen this before. I'll leave it to you to check that this actually holds. But I'll tell you that this form here, multiplying in rectangular form, should be something that you try to avoid to do. So we'll see in just a bit that multiplication is much, much easier to do once we have the complex number in polar form. So if you're going to do multiplication, most of the time it makes sense to first convert into polar form and then do the multiplication. Okay, so let's talk about polar form. We're just defining polar form here. We're not connecting it back to rectangular form yet, but we'll show how to do that in just a bit. But we define polar form for a complex number this way, and I'm specifically calling attention to this fact. If r here is not a a positive real number, so r must be real, and r must be greater than 0. If r is negative, then it is not in polar form. And theta can be anything. Theta is an angle, but typically we like theta to be between, whoops, this is not a requirement, but this is a desire, between plus or minus pi. So polar form is just an alternate way to express a complex number, and we'll see a graphical interpretation of the connection between rectangular and polar form. But I do want to point out here that if you're trying to multiply or divide complex numbers, polar form is the preferred form to have those numbers in. So you may have learned polar form with this symbol. So this is the r that's up here, this is the theta that's up here, and I say we will not use that here. We'll not use it in this set of notes, but in the textbook and in the notes corresponding to the textbook, we will use it. I actually prefer this form, and I'll tell you why. Because that form is a true mathematical form. It behaves exactly like any other exponential, even ones that don't have the j up in the exponent. So once you know the rules of exponentials, then that's all you need to know. All the manipulation of complex numbers come from the rules of manipulating exponentials. Now, unfortunately, if you don't already know the rules of exponentials, then you're kind of in a difficult spot. So you should learn the rules of exponentials. If you're going to be an engineer, and I'm working under the assumption that each and every one of you, since you are putting yourself through this challenging course, wants to be an engineer. So if you're going to be an engineer, you just got to know how exponentials work. Exponentials are everywhere in the world. Stock market. So even if you want to be a financial or business side of the engineering world, exponentials show up. You just need to understand exponentials. So here are the two main rules of exponentials that we'll be exploiting. A to the x, where a is anything, x is anything. A to the y, so the same base, different exponent, multiplied together is a to the x plus y. And then likewise, a to the x divided by a to the y, same base, gives you a to the x minus y. See, this parallel structure here is very easy to remember. So once we have that, we now know how polar form behaves when we do addition and division, or I'm sorry, multiplication and division. So from that, we immediately get that two complex numbers in polar form, if we multiply them, and again, we're assuming here that R1 and R2 are non-negative, then we take the product of their magnitude. So R is called the magnitude, theta is called the angle. So to multiply in polar form, we have the new magnitude as the product of the two original magnitudes, and the new angle, which is the thing next to the j, is the sum of the two original angles. So very simple form. It follows this right here is why we add those angles. Okay, and then some consequences of that. If we take a complex number and raise it to the nth power, we can rewrite it this way. This is just another rule of exponentiation. A to the x raised to the nth power is just a to the nx. And a times b to the nth power is just a to the n, b to the n. Those are just two more rules of exponentials that we can exploit. So we're using both of these over here to get this. So we used this one here first to split it onto the 2, and then we use this one here to bring the n down in front of the theta. So that's another rule. You can memorize it. You should memorize it. And then likewise, if we have z to the 1 over n, playing the same kind of game, we get r to the 1 over n, and we get e to the j theta over n. So we get that kind of result. Now, given this result here, we can see that if we take the magnitude of this product, taking the magnitude of this product, it's the same as taking the magnitude of this, and we then get the fact that magnitude of AB for any two numbers is the magnitude of A times the magnitude of B. Another result that you should just be aware of and puzzle out, right? Magnitude of minus 5 times 3 is equal to the magnitude of minus 5 times the magnitude of 3. So you can verify that that is indeed correct. Well, the magnitude of this is just the magnitude of R1 times R2, taking that as the A and taking this as the B, the magnitude of e to the j theta 1 plus theta 2. Now, we haven't gotten into the details of this yet, but look at this. This is nothing more than a complex number with magnitude of 1 out in front. And when we're taking the magnitude of z, what we really mean is grabbing this thing in front, assuming that it is positive. So this whole thing goes to 1, and we're left with this. And magnitude of R1, that's equal to that. So that leads us to this result. The magnitude of Z1, magnitude of the quantity of Z1, Z2, is equal to the magnitude of Z1 times the magnitude of Z2. And again, these are things that don't necessarily have to be memorized. You can puzzle these out from the first principles. And the way to attack this is to learn those first principles and then do a lot of these examples until it just becomes second nature. And just listen, trust me on this. I know, I'm an old fart, and you don't want to listen to me, and you don't want to take my advice because you don't think I know what's good for you. And in a lot of cases, I don't. But in this case, I do. This is something that's going to haunt you forever. Mechanicals, I'm pretty sure this shows up all over the place for you. ISEs, I'm not quite sure. But I'm pretty sure you'll see these kinds of things in various places. But for EEs and COEs, this is all over the place in everything else you're going to do, especially the EEs. So please, you got to master this. You got to practice this. This is what it means to become an engineer. You have to nail this stuff down. The other part of this is that if we want the angle of the product of two complex numbers, all we have to do is add the two angles. And again, that comes from this result. The angle of this whole thing is the angle of this, and the angle of that is just this theta 1 plus theta 2. That's what this is showing. Okay, so that's multiplication using polar form. Division using polar form, again, just follows from this result up here. So we have one complex number divided by another complex number. We take the ratio of their two magnitudes, and we take the difference of their two angles. And likewise, if we take 1 over z2, 1 over a complex number, that's like this, we can form it. It has a new magnitude that's that, and a new angle that is the negative. So look at that. Whatever theta 2 is, we negate it. So if theta 2 was 45 degrees, we put that down in the denominator, we can rewrite it as this reciprocal is the magnitude, and the new angle not down in the denominator is minus 45 degrees. Okay, so again, these are rules that you'll just need to learn to best way to learn them is through a lot of practice, not just sitting staring at the list of equations and muttering them to yourself and thinking that you know them. Just do lots of examples until you've built those pathways into your neurons. All right, let's look at the connections between rectangular and polar forms. And so you've seen all this before, I'm hoping. It's based upon things that you definitely have seen before, the connection between geometry and trigonometry, and sines and cosines and so forth. So when we think about a complex number in rectangular form, we think about a real part plus an imaginary part, so A plus JB. We can think about each of those individual parts as falling on a different axis. So this is the real axis, and this is the imaginary axis. Now, let me just pause for a moment here and ask you a question. If I say that z is equal to 5, you know that's a real number, but can I also think of it as a complex number? I sure can, plus j0. So notice that anything that lies on this line is a purely real number, but we can think of it as a specific member of the set of complex numbers, just one that has 0 imaginary part. So all the rules that we have for complex numbers must be consistent with the rules that we have for real numbers, since real numbers must also be considered as complex numbers. Okay. So what we're doing here is saying that here's a number, z, complex number. Here's its real part, here's its imaginary part. And so we can think of that complex number as being this point right here on this real imaginary plane, or this complex plane. So this is the complex plane. And we can extract from that this triangle, and in reality theta can be anything. So if theta were over here, this triangle becomes a little harder to extract. So we usually just draw the angle in this quadrant and think about the triangle from there, but we can actually, once we have this triangle drawn, we can extract all the insight for any angle, regardless of where it falls, whether it's acute or obtuse. So from this, we've extracted this, and we can immediately get these conversion formulas. We know that that b here is just equal to r times sine of theta. So that's our old friend from high school, SOHCAHTOA, right? Sine is opposite over a hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. That's the SOHCAHTOA. So this is just taking this opposite over hypotenuse. So sine of theta is equal to opposite over hypotenuse, and we're now swinging the r over to there. So we get this result, and that's this answer right there. So if I gave you r and theta, you can use that equation to find the imaginary part. And likewise, we can find a is equal to r times cosine theta. So once I give you r and theta, you can convert and find a and b. So that's this is converting from polar to rectangular. And notice why we call this rectangular, because a and b are specifying the sides of a rectangle. And then likewise, if I gave you a and b and you wanted to find r and theta, well, Pythagorean theorem allows you to find r given a and b. So that's this equation. R squared is equal to a squared plus b squared. And then again from TOA, tangent of theta is equal to opposite over adjacent, so that's b over a. And if I want to isolate theta, I then have to take inverse tangent, so theta is equal to the inverse tangent of b over a. So again, here's our conversion formulas. Do you have to memorize them? No, they should be pretty much internalized inside you. You can puzzle them out from the SOHCAHTOA if you have to. But again, if you use these enough and you do enough practice, they will be internalized, and that's what I will expect. That's what you need to do to succeed through the rest of the program here. So these two are used for converting rectangular into polar. So, once you have a plus jb, you now know how to convert into r e to the j theta, or vice versa. So you can do this conversion back and forth. Now here's some equations that come out of this. Basically, we're just using the conversions that we just saw. So if I have e to the j theta, the imaginary, or the real part of that is just going to be cosine of theta. There's no, this is 1 here, so we have a 1 there. And the imaginary part is going to be j times 1 sine of theta. And so we have that those two are the same numbers, so we can set them equal to each other, and that's what we have here. And then likewise, to get this one, we can say, well, I'm going to replace j in both places by minus j. That's one way to visualize it. Or the other way to visualize it is that I now have, instead of a plus angle theta, here's minus angle theta. That does not change the real part, but it does change the imaginary part, and it now becomes equal but opposite in direction, so it's negative. So the imaginary part now becomes minus j sine theta instead of plus j sine theta. And these two equations together are what are known as Euler's equations. Now, we can also, and I'm just showing that down here, that e to the j theta and minus e to the j theta, that we can make e to the j theta here by adding cosine theta together with j sine theta. So that's illustrating those. Okay, now the other thing that we have here is if I just take these two equations, I take the equation A and I take the equation B, and I add them together, notice what happens. Those two cancel each other, so I get e to the j theta plus e to the minus j theta is equal to 2 cosine theta. And if I divide each side by 2, I get this equation right here. So that also holds. And likewise, if I were to take these two equations and take A minus B, well, that's like putting a plus and a minus there and a minus there. Now adding those together, these cancel. Those add together to give 2j sine theta. And I can then divide by 2j, and I get sine of theta is equal to e to the j theta minus e to the minus j theta divided by 2j. So these four equations, I refer to all four of them as Euler's equations. Other books may refer just to these as Euler's equations, but I like to include all four of these equations. And so that second pair is illustrated here. If I take e to the j theta and I take e to the minus j theta and I add them together, thinking about this in the way that we think about vector addition, I bring that one up here and I form that other, and that ends up being out here. There's 2 times cosine theta. Okay, so these are just graphical ways of thinking about this. The EEs and COEs will encounter this again in 301 in the fall. So do yourself a favor and spend a little time with this and nail it down now, and you'll be far ahead of the game. In 301, I'll just expect that these things will almost be second nature to you. And we'll be using them to learn other things. So don't leave it till then to nail these things down. Okay, so let's summarize some of the results that we've just seen. We've got our rectangular form, we've got our polar form, and this is showing the connections, the conversions, and this is showing the connections and conversions between the two forms. This is a strict requirement. This is a desired requirement on polar form. Now, here's a warning. If you take, let's say I give you z is equal to minus 3 plus j4, and you take that and you put it into this form to compute theta. So the first thing you're going to do is you're going to say, okay, b is 4, a is minus 3, and now I'm going to take the inverse tangent of minus 4/3. Well, isn't that also the same as minus 4 over 3? So how do I know whether this is, let's say this is Z1, Z2 is equal to 3 minus J4? What do those two numbers look like? Well, one is minus 3 plus 4, so there's Z1. The other one is 3 minus 4. It's over here. There's Z2. They are not the same. And so when you take inverse tangent of minus 4/3, how does your calculator know which of these two angles it should get? That one versus that one? Well, your calculator doesn't know. So whenever you give it a negative number, it makes the assumption that the top number was the negative one. Or in other words, the imaginary part was the negative one. So it always assumes that the real part is positive. Now this is only if you're using your calculator to do this explicitly, by first forming this ratio and then doing inverse tangent. Many calculators, in fact virtually every calculator that any student in this class has, likely has a separate way of doing rectangular to polar conversion, where you tell it explicitly, this is the real part, this is the imaginary part, now please convert into polar form for me. If you do it that way, there's no problem. But if you do it this way, where you first form the ratio and then take the inverse tangent, your calculator will give you the wrong answer whenever the real part is less than 0. So in other words, here's quadrant 1, here's quadrant 2, here's quadrant 3, here's quadrant 4. Anytime it lies in quadrant 2 or quadrant 3, anytime you have a complex number in quadrant 2 or quadrant 3, your calculator, when you calculate this way, will give you the wrong angle. But you can fix it. You can always fix it by adding or subtracting pi. Now I erased what I had earlier, but if you remember, one of them was over here and one was over here. So this was 3 minus J4 was this one. That's 3 minus J4, and this was minus 3 plus J4. This is the one that your calculator would give you even if you were calculating for that one. That's down here. Notice that that is 180 degrees or pi radians away. So that will always be the case, and all we have to do is add or subtract pi. And how do we know whether we add or whether we subtract pi? Well, we want to end up, we wish, it's not a requirement, but we would prefer to end up with an angle between minus pi and plus pi. So in this case, we would add pi to get there. Subtract pi, so this is actually minus, positive angles in that direction. That's adding pi. If we subtracted minus pi, we would end up physically at the same point. We would just now have a more negative angle. So we can always add or subtract pi to fix this, and I'll show you some examples in a little while. The best thing to do is make sketches and see where things lie. I cannot tell you how many times I've taken off many points on exams or an error that could have been simply recognized and avoided if the student had just drawn a little diagram. Draw the diagram, look at where your real and imaginary parts are as given, and make sure that your angle that you finally compute makes sense. It should put you in the right quadrant, in the correct quadrant. So, as I said, we'll do some examples on this in just a little bit. Okay, the concept of conjugate of z. Some books denote it as z star, some books denote it as z bar. Same concept regardless. Let's say that we have a complex number given in rectangular form. The conjugate of z is everything's the same except we change the sign here. Okay, so if we had 5 minus J3 z conjugate is equal to 5 plus j3. We've just negated the imaginary part. Here it started off negative, we negate it to get a positive. In polar form, again, all we have to do is change the sign out in front of j. So we put a negative out there. So if we did have z is equal to, say, 3e to the minus j pi over 3, z conjugate is equal to 3e to the plus j pi over 3. So all we have to do is negate it. Some properties of conjugation are the following. If we add the conjugate to the original, the imaginary parts cancel and we're left with 2 times the real part. So if you were to add these two things together, see that the j part cancels and we're left with 10, which is twice the real part. And likewise, if we multiply them together, we get, if you expand this out, you'll see that you get a squared plus b squared, and that's nothing more than the magnitude squared. Another way to see that is using these results. We have z times z conjugate is equal to r e to the j theta times r e to the minus j theta, which is equal to r squared, times e to the j theta plus minus theta is equal to r squared e to the j 0. Anything to the 0 is 1, and so we're left with r squared, and that is the magnitude squared of the original z. So again, these are some rules that are handy. Now, many of you have been taught that the way to deal with complex numbers that are, say, 5 plus j3 over maybe 2 minus j2, if you want to simplify that, you've been taught to multiply top and bottom by the conjugate of the bottom. So 2 plus j2, 2 plus j2. And the advantage of doing that, you end up getting something that's complex up on the top, and on the bottom you just get this a squared plus b squared. So in this case it's going to be 4 plus 4, which ends up being over 8. So it makes a real number in the denominator. That's fine, but I would encourage you to also know the other way to do this that we talked about. Another way to do this is to convert top and bottom to polar form. So you would convert this to r1 e to the j theta 1 all over r2 e to the j theta 2, and then you'd get r1 over r2 e to the j theta 1 minus theta 2. It may seem like a little bit of extra work here, but for circuit analysis and in 301 system analysis, this is our preferred final form, and so it makes sense to first do this conversion and work from there. So it's not wrong to multiply top and bottom by conjugate and work from there, but it doesn't necessarily bring you to the spot you want to be at the end. So you should know about that, but don't just blindly fall into using that. So here's a summary of all the results that we've talked about so far. I'm not going to go through that right now. This is just presented to you to have a one-stop shopping spot to get all of these results. And hopefully I haven't made any typos here, but you might want to correlate these to places where you've seen them in the previous charts, as well as some textbook or something like that. And here's a few tricks that we can use. If we encounter 1 over j, we can replace it by minus j. How do we prove that? Well, 1 over j, converting it into polar form. How do I know that this is the polar form of j? I don't have to do any calculations. Here's real imaginary. J, so I'm converting j into that. J is just this number right here. It's at the value of j, so its magnitude, its length is 1 times j, and its angle is 90 degrees, which is pi over 2. So it's 1 at an angle of pi over 2. So it's just e to the j pi over 2. So that one in itself is worth knowing, and that's right down here. So we'll get to that in just a little bit. So 1 over j is equal to 1 over e to the j pi over 2. And now we're going to use the form for dividing complex numbers. The top here is really just 1 e to the j 0, right, since e to the j 0 is 1. So we have the ratio of their two magnitudes, 1 over 1, which is 1, and we have the difference of their angles, and we see that that boils down to e to the minus j pi over 2. Yes, these are the things. These steps are things that you should know how to do and be able to do. I'm showing you them here. You should learn them. You should practice them. They are crucial to what you need to do in this course and subsequent courses. And now, using Euler's formula to expand this, we get this. And we now know that, we know that cosine of pi over 2, cosine of 90 degrees is 0. Sine of pi over 2 is minus 1. And so we get 0 minus j, which is just equal to minus j. And so we can prove these other ones similarly. We can see that minus 1 is equal to e to the plus or minus j pi. And we can prove that using Euler's formula. Or again, we can just see, here's the real axis, here's the imaginary axis. Where's minus 1? It's right there. We're talking about that. What's its magnitude? Well, that's the length of this. So length of 1. What's its angle? Well, I could go plus pi, or I could go minus pi, either one. So 1 times e to the plus or minus j pi is equal to minus 1. So be aware of that. When you see this, it can be smashed down into minus 1. Or when you see this, you can smash it up into this complex number in polar form, which can then combine. And this one we've been using on and off here as we've gone through this, and this one we've seen again. Again, we can prove both of those things using strict mathematics, which is good, but again, all of this gets tied back visually to this complex plane. Here's the real and imaginary. So 1 is over here. It's at an angle of 0 with respect to the real axis. J is up here. It's at an angle of pi over 2. Minus j, for this one, it's down here. It's an angle of minus pi over 2. So none of these really have to be memorized. They all can be visualized from this figure. And that's what I would encourage you to do. And then finally, this is something that stymies many, many students, gets them into a lot of trouble. And I ask this over and over in 301. I purposely put it on the quizzes and exams because I make a big deal out of it, because students keep messing up on this, and this is the kind of thing that could end up sending, say for example, a millions of dollars worth of space equipment off into the unknown, unknown where it went to. So this is a purely real number here. It's a plus j0, and I'm asking what is its angle. So what is the angle of 5, or what is the angle of minus 3? What are those things? Well, we already know real numbers are complex numbers. So if we can ask what is the angle of a complex number, we should be able to ask what is the angle of a real number. Well, we know that real numbers must lie on this real line, right? So there's only two options. If it lies over here, it's going to have an angle of 0. And if it lies over here, it'll have an angle of plus or minus pi. Both of those are correct, plus pi and minus pi. So when a is positive, it lies over here, and the angle is 0. When a is negative, it lies over here, and its angle is either plus or minus pi. Okay, so the angle of 5 is equal to 0, and the angle of minus 3 is plus or minus pi. All right, now here's a bunch of examples. We're given a complex number in rectangular form, and we're asked to convert to polar form. So there's the problem statement. Everything else is what I would expect you to be able to do on your own fairly rapidly. We want to convert to polar form, so we need this. We need to find the magnitude of z. We need to find the angle of z given this form. So the magnitude of z, here's our formula, square root of minus 4 squared. Now listen to me carefully. This is source of problems here, right? Listen, when I take the thing to put inside here, I do not bring the j along. I get the 3 and the minus, but I leave the j behind. So minus 3 squared. And I don't even really need to drag the minus along since I'm going to be putting that in the square, but I'll need that in another spot. So I end up getting square root of 16 plus 9, square root of 25, which is 5. In this case, it works out to a nice round number. To find the angle, I'm going to take the imaginary part. Now here's where I do need, the negative. So I have a minus 3, and I have a minus 4 that goes in there. Now, I'm set up to make an error here if I'm not careful. My real part is negative. That means I'm over here or over here. I'm somewhere in quadrant 2 or quadrant 3. That's going to be a problem if we're not careful. So when I form this ratio, minus 3 over minus 4, I get that's equal to 3/4. So how is my calculator going to know whether I'm talking about something over here or something over here? That is 180 degrees or pi radians away. It won't know. So it will actually give me the inverse tangent of 0.75, which is 0.64 radians. That's wrong. I have to subtract pi off, so it's giving me this angle, 0.64. It's all illustrated down here. So it's giving me this angle, which is the wrong angle. And to keep my final angle between plus or minus pi, I will take plus 0.64 and subtract pi from it, and I end up getting this angle down here. So there's where I really want to be. And that ends up being minus 2.5 radians. Remember, minus pi is approximately minus 3.14, so this is within plus or minus pi. Good. Okay, so now I know that I can write my z, and this is an approximation, but we'll live with it, in polar form as 5 times e to the minus j 2.5. I'm going to ignore that phone call for the moment, and I'll get it later. Okay, so example 1b, again given complex number, very similar to what we had before. Before we had minus 4 minus j3. We're going to convert to polar form. So this is the problem statement, and everything else I would expect you to be able to figure out on your own. So we're going to use this as our polar form. We need to use our conversions to find the magnitude and angle. So the magnitude works exactly the same. The fact that this is plus rather than minus does not change that. But now we have a 3 over minus 4. So our calculator thinks it's over here somewhere. Actually, that should be a minus in front there. And now we're going to add pi radians so that we end up back over here, and this is in between plus or minus pi. So now we end up with plus 2.5 radians. So we can state that this is rectangular form, this is polar form, those two things are equal to each other. Now I'd also like to point out that notice that example 1 and example 1b are conjugates of each other. We had minus 4 minus j3 in 1a, and in 1b we had minus 4 plus j3. And the thing that we know about conjugates are their angles are equal but opposite. So we had plus 2.5 radians here, and in example 1a we had minus 2.5 radians. So once we knew the answer for A, 1a, recognizing that because this is plus now where it was minus, everything else is the same, recognizing that we have the conjugate of that, we could have jumped immediately to this without any calculation. Those are the kinds of insights you need to be able to do, and you need to build that skill. Okay, example 2. Given something in polar form, convert to rectangular form. So here's the problem statement. Everything else is something you need to do. we're going to use Euler's formula, which basically allows us, or it's really the conversion into the rectangular to polar, or polar to rectangular conversion. We need to know the magnitude, we need to know the angle of z. So by inspection, we come up here and we say, okay, this is in polar form, so the magnitude of z is just equal to that part, so there's 3, and the angle of z is just equal to that part. And if there were a minus sign out in front, we would have to carry that along. Okay, so we have the angle of pi over 4. We need to know cosine of pi over 4 and sine of pi over 4. So those are that. Your calculator will give you 0.707, but that's an angle that it's probably a good idea for you to just know the answer for. Pi over 4 is 45 degrees, by the way. So we now have, using these results, we have 3 times square root of 2 gives us 3 over square root of 2, plus j, 3 times 1 over square root of 2 gives us that result. So we've now converted from polar to rectangular, and as a final check, it makes sense to say, well, pi over 4, that's just this angle here, that's a positive angle. So our real part and our imaginary part should both be positive, and they should both be equal to each other. I didn't draw this picture very accurately, but since it's a 45-degree angle, they should be equal to each other, and they are indeed, the real and imaginary parts, equal to each other in this case. Example 3. Given this, write it in polar form. Now you might think, gee, it sort of looks like it's already in polar form, but it's not. It is not in polar form because we have some number times e to the minus j. This part is in polar form, but this is not a magnitude, not a real number out in front, certainly not a positive real number. So our strict definition is polar form is some real number times e to the j, some real number. So if it's not in that strict form, then it's not in polar. So we really need to view this as the product of two complex numbers. The j times the part that's left. So here's z1, and here is z2. And so now, to do multiplication, it makes more sense to convert this, which we can think of as being in rectangular form, into polar form. Now we already know that j looks like that, therefore j is equal to e to the j pi over 2. That's one of our tricks that we had, or you could work this out in detail and find out that same thing. So we now have z is equal to, that's what's given. We've now converted the j into this, kept that here, and now we're going to use our rule for multiplication of polar form complex numbers. 1 times 1, there's a 1 out there, there's a 1 out there, it gives us 1. And then we add the angles, pi over 2 plus a minus pi over 2. Those all go to 0. So we have 1 e to the j 0. That's equal to 1. The whole thing boils down to 1. So we have that this complicated thing here is nothing more than 1. It's a nice, lovely little thing to show how you can write down the number 1 in a very complicated fashion. In fact, there's a nice little way of writing down, I think it's the 5 most important numbers in mathematics. Let's see if I can remember how it goes here. E to the j pi, I know that that's actually equal to minus 1, plus 1 is equal to 0. So there's a nice little equation that links 5 of the most important numbers in mathematics. E, pi, j, 1, and 0. So this is actually equal to minus 1, right? E to the j pi. So interesting little aside there. Example 4. Now this is very similar to the kinds of manipulations that we'll need to know how to do for circuits and for subsequent courses in electrical and computer engineering. given this ratio of two rectangular form complex numbers, find the magnitude and angle of the resulting number z. So we're going to use these two results here. So first, it makes sense to just let's find the magnitude first. So the magnitude of the whole thing breaks down to the ratio of the magnitudes. And so now we're taking the magnitude of two separate rectangular form complex numbers. So we apply that formula and we get square root of 13 over the square root of 13, which gives us 1. So we know that z is going to be equal to 1 e to the j something. We don't know what that is yet. Let's find what that is. So we take the angle of the whole thing, which by our rule is take the angle of the numerator minus the angle of the denominator. And when we do that, we take this, put it into our calculator. No problems there, since the real part is positive. Whatever our calculator spits out is correct. Here we're going to take inverse tangent of minus 2 over 3. Our calculator does not know that the minus actually belongs to the 3. And therefore, our calculator spits out minus 0.58, to which we add pi. And now we're going to subtract that whole quantity from here, and we get 1.57 radians. Now, you get good after a while to recognize things like pi over 2 and pi over 4 when they get truncated to just a few decimal places. 1.57 tells me that I should expect that the real answer is pi over 2. So in reality, this thing is 1 e to the j pi over 2, which is also just equal to j. So that whole thing can be boiled down to j, believe it or not. Okay, here's another example. Here we're looking at complex numbers that depend on unknown variables. So R1 is like a resistance, C is a capacitance, R2 is a resistance, L is an inductance. And once we're a little further into Chapter 8, you'll know where this example comes from and why we're interested in doing it. But for right now, just take R1, R2, C, and L as positive real numbers. So we're asked to find the magnitude and the angle of this complex number. Obviously, those are going to depend on the R's, the C's, and the L's. So let's do some common manipulations here that will help us get to a point where we can find the magnitude a little easier. So here we see that we've got a j in the denominator, so this top part isn't even really in rectangular form yet, so we have to worry about that first. And so one common trick when you see a j in a denominator is to multiply through top and bottom by jc in this case. And when we do that, this jc will end up canceling that jc. So we get that. So we're going to pass the jc through. We get all of these terms. And then we see here that this actually gives us 1, so we'll write that first. That's a real part. And j r1c comes over here. And here we see a j times a j. That gives us a minus 1, so we'll pull that out front. That's the real part. Plus a j r2c. So now what do we have? Look, we have now something that is rectangular form on the top, rectangular form on the bottom. We're all set. Magnitude of z is the magnitude of top divided by the magnitude of the bottom. Plug those into our formulas. 1 squared r1c. Remember, do not take the j along. If you take the j along, you're going to get the wrong number, or the wrong answer, the wrong magnitude. Likewise, plugging in here and working it all out, just doing a little bit of algebra. Here we end up with an L squared C squared r2 squared c squared. We can factor out the c squared. It would still be underneath the square root sign. Pulling that out with the square root ends up giving us c. So, all those manipulations that you need to learn in high school, you still need to know those. And in my opinion, probably at this point you're saying, no, I don't want to know your opinion, but here it is anyway. My opinion is that the thing that brings students down the most in these courses, circuits and my signals and systems class, is not their inability to grasp the bigger concepts. It's their inability to do the simple high school mathematical manipulations. I don't know if that's just because you learned them, your learning of them was fragile and now you just don't have the time to catch back up, or what, but if you want to help yourself get better grades in this course, as well as my 301 course, spend a little time going back and reviewing some of the simple mathematical concepts and rules, and then you'll be able to do much better. So we now have a form here for the magnitude, and now all we have to do is find the angle. So angle is the angle of the top. So we're going to go back to here. Here's angle of the top minus the angle of the bottom. So we have the angle of the top minus the angle of the bottom, and now we're going to do our inverse tangent. Here our real part is definitely real and positive, so we can just write it like that, r1 over c, or r1c over 1 minus the inverse tangent of this ratio. The c's cancel when we put them over each other, but notice that our real part is negative. We know that L is a positive number, and so we have to add pi. The real part is negative. We could also subtract pi there, but this thing's going to end up over here. Actually, this is wrong. We should subtract pi. So I made a typo there, so that shouldn't be there. We should subtract pi from that. Adding pi goes counterclockwise. Subtracting pi goes clockwise. Here's example 5b. Notice that this is actually the same example. We're just going to do it a different way. So here we're going to, instead of multiplying top and bottom by jc, we're going to recognize that j, 1 over j is equal to minus j. So we can replace that 1 over j by the minus j. Leave the c down in the denominator. And now we do have rectangular form in the top and in the bottom. And so now we can find our magnitude. Magnitude of the top divided by magnitude of the bottom. Here's the magnitude of the top. Here's the magnitude of the bottom. And after a little bit of manipulation, we get something that looks like that. Find the angle. Angle of the top minus the angle of the bottom. And notice that now we don't have any corrections to make, and we just progress to this. And these things, even though they look different in form from what we got for example 5a, they are exactly equal to each other in numerical values. So this gives you a little review, a little exposure, maybe helping you see things in a new light that you hadn't seen before. Again, I know I've been harping on this. You're probably sick and tired of hearing me. But listen, I'm a dad, so I'm used to harping until my daughters can't stand it anymore, so I might as well do it with you. These are the things that are the steps to your success in this course and in subsequent courses in your program. Build a strong foundation now so that later when these things crop up over and over again, you'll be able to do them without thinking, do them correctly without thinking, and you can concentrate more on the more advanced ideas that these are used to support. Oh, we've got another one here. I don't know how this happened. 17 out of 16. I guess I added another example but forgot to update the number of slides. So this one is just showing same kind of thing. We got a minus 1 everything's already in rectangular over rectangle, so we can treat this as a complex number. Yes, I know why I put this one in here. So we have magnitude of -1. Well, again, magnitude and absolute value are the same, right? We're using the same symbol. Doesn't matter if we put in a complex number or if we put in, some real number. It's the same concept. So magnitude of -1 is 1. Look at it on the picture, right? Here's -1. Absolute value or magnitude of this is just how long that length is. It's equal to 1 if that's -1. So there's our 1. Use the standard square root of sum of squares in the denominator, and we now have a formula to see how the magnitude of this complex number here depends on R2 and L. Now to find the angle. This is really why I put this in here. The angle of -1, well, that's just this angle here. So it's plus or minus pi, either one. And then we have minus the inverse tangent of L over